Okay, good morning. Today we're going to continue learning about Newton's laws of motion and also about something called terminal velocity, which hopefully you've already seen a little bit about from the video that I posted on Google Classroom. Now, we're going to look at the story of a skydiver in this video, where I'm going to be talking about the forces that the skydiver experiences from the moment that he jumps out of the plane, as he falls through the air, as he continues falling through the air, as he then opens the parachute, a little bit later with the parachute open, and eventually comes to ground. So we're going to be identifying what forces are acting on that skydiver, and then looking at how that might affect their motion. So let's start off with number one. Okay, number one is the instant he jumps from the plane. So just before this, he's going to be standing on the plane, and his weight is going to be acting down, but it's going to be balanced by the normal reaction force acting up. But the instant that he pushes off the plane and he's just standing in midair for that second before he starts to drop, okay, there's no longer going to be the plane pushing back on him. So we are going to draw in that one of the forces acting on him is going to be weight acting downwards. So I'm going to draw an arrow for his weight. Okay. I'm also going to write next to it that this is his weight, and I'm going to make up a number for it. Now, if you can remember from last week, the weight and the mass are linked. Okay, and if you know your mass on the Earth, you can just times that number by 10, and you can get the weight. So I know here on Earth, I have a weight of about 800 newtons because my mass is about 80 kilograms. So I'm going to put this in as a weight approximately the same as me. Now, as he falls, what we're going to find is that actually I can keep reusing this because his weight doesn't change. So a bit later at number 2, weight is the same. A bit later at number 3, weight is the same. A bit later at number 4, weight is the same. A bit later at number 5, weight is the same. Let's just move that a little bit. Make sure it's in the right place. Should be from the center of the person. So like that. And then number 6. Surprise, surprise. Weight is the same. So as you fall, okay, it doesn't matter how quick you're moving, whether you're stationary, moving really fast, moving slowly, your weight is always going to be the same because it depends on your mass and the strength of gravity. And gravity is roughly the same everywhere on the Earth. So actually, our weight shouldn't change as we fall. So we've added the weight to all of them. We're saying that there's always going to be a weight of 800 newtons pulling you directly down towards the center of the Earth. What I want to do is identify, are there any other forces that are going to be acting? Now, we said in number 1, before the skydiver jumps out, the weight is going to be balanced by a normal reaction force. This is the idea that the skydiver pushes down on the floor, but the floor pushes back on him. But once he's jumped, that's not going to be there anymore. Now, as well as not having normal reaction force, there's going to be no air resistance, because air resistance is a force that you experience as you hit air particles, as you're falling or moving through the air. Now, at the instant he jumps, he's not going to be falling downwards. Okay, so there's no air resistance too. There's no upthrust. People always ask me about what upthrust is. Upthrust is the upward force experienced if you're submerged in a fluid, okay, like water. But actually, there's pretty much zero upthrust when you're in air. And actually, this is the only force, significant force, we need to consider here. So there's only one force acting downwards. Now, because of that, I'm going to write that we have unbalanced forces. Okay, and if we have unbalanced forces, we should be able to work out the resultant force. Well, because there's nothing to balance the weight, the resultant force is 800 newtons down. Okay? And therefore, that skydiver is going to start accelerating downwards, which is fairly obvious because we know if we drop somebody out of an aeroplane or we drop anything, that starts to get faster as it falls. And the reason it starts to go faster as it falls is the weight is acting down, and to begin with, there's no force opposing it. So obviously that skydiver is going to start falling downwards. And as he falls down, his weight is still going to pull on him. But we're going to have a change here. And that change is going to be that now the skydiver is passing through the air, and he's going to be hitting all these air particles that are sitting underneath it. Now, as he hits the air particles are going to exert a force on him, and they're going to be pushing him upwards. So I'm going to draw an arrow upwards. I'm going to make my arrow small though, okay, because at this point, he hasn't been falling very long. He's not hitting that many air particles every second, okay? And therefore, the air resistance is going to be quite small. So I'm going to write in here that we've now got air resistance acting because he's moving. I'm going to make up a number for this. Oh, I can't spell. I'm going to make up a number. I'm going to say 300 newtons, but we can make any number, I guess, in there. Now, this is a force due to the moving object passing through the air, colliding with the air particles, and then pushing back on him. Now, do we have balanced or unbalanced forces here? Oh, clearly, they're still unbalanced. And because they're unbalanced, again, we can say, what's the resultant force? Well, the resultant force here is 800 minus 300, which gives me 500 newtons. And again, I should give a direction in a downward direction. Okay, so it's an unbalanced force. There's an unbalanced resultant force of 500 newtons down. And what's that going to cause him to do? Well, he's still going to accelerate. It's going to be another accelerating, okay, downwards. It's going to continue getting faster. So, skydiver continues falling downwards, getting faster and faster, still passing through all these air particles, still hitting it. In fact, now, because it's going faster, it's going to be hitting even more air particles every second. Okay, and because of that, we're going to get an even bigger force of air resistance, because the faster you go, the bigger air resistance gets. So this arrow's got bigger than last time. Okay, and it will keep getting bigger until eventually that force of air resistance gets so big that it balances the weight. Okay, so you notice now I've got two arrows the same size, okay, and my numbers are the same. So at this point, we have balanced forces. If I wanted to calculate the resultant force this time, it's going to be 800 minus 800, which is equal to 0. There is no resultant force. Okay, we've got balanced forces. Now, Newton's first law told me what could happen in the event of balanced forces. There were two possibilities. Either it's going to remain stationary or it's going to continue at a constant speed. And the situation determines which is going to happen. Was the object moving before the forces became balanced, or was it not? Well, in this case, clearly the skydiver was moving before those forces became balanced. So what we're going to write then, it is going to continue at a constant speed. And we have a name for that constant speed. Okay, it is called terminal velocity. Okay, terminal means kind of final, velocity means speed. So this is its final speed. If nothing else were to change about this situation, then the skydiver would keep falling at that speed until it hit the ground. Okay, so if you dropped from an aeroplane at 5,000 meters, or you would drop from an aeroplane at 10,000 meters, okay, the final speed you would reach would be the same. You don't keep getting faster until you hit the ground. Okay, you get faster until your air resistance balances your weight, and then you will continue at that same speed. Now, this terminal velocity is going to be pretty fast. If the skydiver hits the ground at that speed, then they're going to get squashed. Okay, so what the skydiver does, we go up to number 4, is they open their parachute. Okay, now when they open their parachute, suddenly we get a large increase in surface area. And this is the whole point of the parachute. Now, what that means is that suddenly, because we've got this huge surface area, there's way more air particles that we can hit at the same speed. So all these air particles are suddenly going to be acting upwards, and our air resistance is going to become huge. So here we go. Here's my air resistance. It's really big because we were going quite fast already, and now we've increased our surface area. Now I'm going to say that we've increased our air resistance, and I'm making up the number again, to something really big, like 1,200 on here, okay, compared to the weight of 800. So again, we've got unbalanced forces, okay, and we can work out the resultant force. The resultant force here is going to be 1,200 minus 800, which gives me 400 newtons as my resultant force, this time in an upward direction. Now, people often get confused by this and say, the resultant force is an upward direction, so the skydiver is going to move upwards. Well, the skydiver is not going to move upwards because he was already moving in a downward direction. So the skydiver motion was already this way, downwards. Okay? So it was already moving downwards. And now it's moving downwards, but we've got a bigger force in the upward direction. So what we're going to find is that this causes deceleration, okay? Because deceleration occurs when the resultant force acts in the opposite direction to the way that the object is moving. So it's still going to continue moving down, but deceleration in downward, we say, while moving in the downward direction. Okay? Now, sometimes you see on videos where a person opens a parachute and they appear to start moving upwards in the air. Okay, now they never really move upwards in the air. Okay, the reason why it looks like that is because whenever you see the video of someone skydiving and opening a parachute, that video is taken by another person who's falling with them. Now, while the person being videoed opens their parachute and slows down a lot, okay, the person who's videoing hasn't opened their parachutes and continues plummeting at a really fast speed. So you've got two people falling together. One continues falling really quick, the other slows down, and it looks to the person videoing that that skydiver has moved up into the air, but it hasn't. Okay, all it's done is continued moving downwards, but at a much lower speed. So the skydiver is now decelerating, so it's slowing down. And as it slows down, it hits less and less of these air particles. Okay, so let me draw some of these air particles back in again. So now we're hitting less of them per second because we're slowing down. And as we hit less of them, that's going to mean that our force of air resistance is going to get less and less. Okay, so it was 1,200. Okay, now it's going to get less. I'm going to say that eventually it's going to get so low that it's going to balance the weight again. Okay, so the air resistance now balances the weight, just like it did before. Now we've gone to balance forces again. Now these balance forces are going to give us a resultant force of 0. Okay, the resultant force is going to be 0 because they completely balance each other. So what's that object going to do? Is it going to stay stationary in the middle of the air, or is it going to continue moving at a constant speed? It's going to continue moving at a constant speed because it was moving before the forces became balanced. And what are we going to call this constant speed? Well, just like last time, we're going to call it terminal velocity. Now, this terminal velocity is going to be a slower terminal velocity than one we had in picture number 3, because we've now got a parachute open. We have a much greater surface area, which allows us to hit lots of air particles and keeps this terminal velocity low. But just like in 3, the air resistance is balanced by the weight. And then let's go on to the final one. Now, as soon as the skydiver hits the ground, there's going to be suddenly a big upward force, which is going to cause him to decelerate and slow down until eventually they stop. I want to think about a few seconds after that, after he's safely landed. Now, if he's safely landed, then we know that he is stationary. Okay, and if he's stationary, we know that there must be balanced forces acting on that object. So we're going to kind of move backwards through this one. Now, if there's balanced forces, that means the resultant force is equal to 0 newtons. Okay, but at the moment in my diagram, I've got 800 newtons acting downwards, but I've not got anything acting upwards. So I better add something to balance the forces. Okay, I know it's going to be 800 newtons upwards, because if it wasn't, it wouldn't be balanced. But what causes that force? Because it can't be air resistance, because the object is no longer moving. So if it's no longer moving, it can't be hitting air particles, and there can't be any air resistance. So what's the force then that's causing this? Well, this force is my normal reaction force. Okay, and this is because the skydiver is now standing on the ground. His weight is pushing down on the ground, and the ground is pushing back. Okay, so this is from Newton's third law of motion. And every action has an equal and opposite reaction. The weight pushing on the ground is the action force. The ground pushing back on the person is the reaction force. Okay. I hope that helped. Okay, what I'm going to ask you guys to do now is to have a go at a nugget on Century Tech and do the little assessment at the end. Hopefully, show that you've understood this. Any questions? Then write them in the stream or send me an email, please. Thank you.